So now we are discussing about the Corey-House synthesis, by which we can produce the different kinds of alkane what we want to produce. So now in this Corey-House synthesis, there will be a new reagent which is called Gilman reagent. Okay, before this we knew already about the Greek nut reagents by which we can produce alkane easily with the reaction of any acidic hydrogen. It will produce the alkane. But now move on the Corey-House synthesis. In this Corey-House synthesis, we see that is an organic reaction that involves the reaction of a lithium diorganyl cuprate. So here we see that the lithium diorganyl cuprate R2CuLi. So this is lithium diorganyl means 2 alkyl, and there is one copper for this cuprate. So this name is lithium diorganyl cuprate R2CuLi with an organyl halide, that means Rx. This is organyl halide or alkyl halide. So if you react with these two, one is lithium diorganyl cuprate and other is alkyl halide, this will form that R plus RCu plus LiX. So this is the alkane, and this is the alkyl cuprate, this is the lithium halide. So this method is better than Woods reaction, because in the previous Woods reaction we saw that by Woods reaction we can only produce the even number of alkane, even number of carbon alkane. But in this reaction, in the Corey-House synthesis, we can produce what we want. So is because it's depend on what you take in this R2, that means alkyl group, and this alkyl group. If you take this two different in your choice, you can make easily, prepare easily the you want or choice of one alkane. So this is the main important fact of the Corey-House synthesis, what we use this reaction. So before this, first of all we have to prepare the R2CuLi, that means lithium diorganyl cuprate. This is called the Gilman reagent. So we have to prepare this first of all, then with this reagent we add alkyl halide. By this we can produce or prepare alkane what we want. So the preparation mechanism of Gilman reagent is mainly in this first step. In these first steps, there is one, we need the alkyl halide. We react with lithium, so this will form the alkyl lithium, that means RLi plus lithium halide. So first of all, in the pieces of dry ether, this reaction will occur. So by this reaction we can easily produce alkyl lithium reagent. This is the first step. And then second step, and the lithium dialkyl cuprate, also known as Gilman reagent, is prepared from alkyl lithium by treatment with cuprous iodide in a transmetallation reaction. That means we previously produced the lithium lithium alkyl lithium, and we react with this with copper cuprous iodide. This will form the what you want, lithium diorganyl cuprate. So you see that just lithium and this iodine react with each other. So this will form lithium iodide, and the other form R2CuLi, which is our main concept of reagent. This is Gilman reagent, by which we can produce our desired alkane. So now if you want to produce this last step of alkane, so before we produce that, the alkyl lithium cuprate, or lithium dialkyl cuprate LiRCr, if you react with this alkyl halide Rx, so this will form R prime Actually these are replaced in this X, so this will form RR prime plus RCU. So there is RCU plus LiX, lithium halide. So we see that if you react the lithium dialkanyl cuprate with alkyl halide, this will form first alkyl halide, then alkyl cuprate, then lithium halide. So this is process, by this process we can easily produce any kind of alkane. So here we see that there is also an explanation of by the speaker of a skeleton formula. So in this page we see that the first steps organolithium formations. So here you see that first step we need alkyl halide with react with lithium, so this will form alkyl lithium. So this is the our alkyl halide in this uh, skeleton formula. So here is the alkyl halide is bromine. So if you react with this lithium, so this will form the organolithium reagent or alkyl lithium. So this is the first step or so for of produce organolithium. Then second steps transmetallations. If you react is further, here as you see that the cuprous iodide or cuprous bromide, or it can be cuprous chloride, it doesn't matter. So here you see that cuprous bromide, so the lithium will replace it by copper. So there is from the organocopper reagents. Here we see that the lithium is replaced by copper, so there is a transfer of the metal. That's why we call this process is the transmetallations of copper salt. So this process is called transmetallations. So Gilman found that adding a second equivalent of an organolithium RLi to an organocopper reagent makes an organocuprate reagent, which is far more reactive and useful. So here we produce before the organocopper reagent, but this with this organocopper reagent, if we add the organolithium, this reactivity is increased than the before, and it also useful for us. So we use this, which is called the Gilman reagents. So you can also produce, you can also represent this by R2 Cu Li. So this is our Gilman reagent. If we add Gilman reagent with any alkane and alkyl halide, this will form alkane. So by this Corey-Howe synthesis we can produce any kind of alkane. So here is we see that some examples. So this is the R2CuLi, that means dialkyl lithium dialkyl organocuprate, react with the alkyl halide. This will be alkyl halide, this will be, we see that aromatic, this is also an aromatic, and this is alkene. So in every reactant, the production, we see that the X or halogen is replaced by alkyl group. So see that the halogen is replaced by alkyl group, so this will form our alkane. So by this you can also produce the different kind of 1 degree, 2 degree, 3 degree. So first main mechanism is just this halogen, which is replaced by this R. By this we can produce any kind of alkane. So there is a discussion about Gilman reagents versus Grignard reagents. So we can produce alkane by Grignard reagents and Gilman reagents, both we can produce the alkane, but there is something different between those reagents, because the difference between is that the organocuprates do not generally add to aldehyde ketones or esters. They do participate in the substitution and conjugate addition reaction that Grignard and organolithium reagents typically don't do. So here we see that Grignard reagents, that means RMGX CH3MgCl, add to ketone. So this is the ketone, and others, it can be other some things carbonyl groups, that means there is a effective structure of molecule is CO double bond O. If you add this with Grignard reagent, this will react, and this reaction will be an addition reactions. So this is our product. But Gilman reagents or organocrepeps do not react with these carbonyls, so there is no reaction. So what is the reason behind it? That the Grignard reagents react with carbonyl, but the organocrepeps or the lithium diagonal cupet, why can't react with the carbonyls group? So before this, you let's put a double bond next to the ketone and run the reaction again. So we put a double bond here, see that before there is no double bond. So we put a double bond here, that's why this is the new form of complex. So here you see that our carbonyl group CO, besides the carbonyl group attached with the carbon, we call it, this is alpha carbon. Those carbon who is attached with the alpha carbon, this is called the beta carbon. So here in this alpha beta carbon has a unsaturated, because there is a double bond now, but before there was not a double bond. That's why before the alpha carbon and beta carbon was saturated, but here the alpha and beta carbon is not saturated because of the double bond now. So for this double bond, the Grignard reagents react with it easily, but here we see that the organocrepet also reacts with these carbonyls when you put this with a double bond. So thus the conclusion is the organocrepets reacts with carbonyl when there is a conjugations, that means there is a double bond in this main cycle. So this will participate in this conjugate addition, but Grignard reagents participate with the simple addition, but organocrepets reagent participate with the conjugate reaction. So there is a reason behind it. So the reason it is, we know that we know already the resonance, we know the resonance, yes. So this is our main carbonyl group. Here you see the electronics, oxygen is more electronegative than the carbon, so that's why the electron towards the oxygen, so the oxygen will be negative, and this carbon will loss of one electron, so that's why this will be partially positive. If this partially positive, this electron try to move here for the charge equivalency, so this will form that like that. There is single bond oxygen minus, this will be positive, so this will create a bond here. So there is a double bond, and this is the oxygen minus. But now this carbon is lack of electron, so this will also form positive charge. So by this equivalency we can say that by this resonance, oxygen is del minus, and this is the del plus form, and this carbon is also the del plus form, that means positive form. So here is this is the resonance hybrid, and this resonance hybrids we see that the two carbon, this carbon and this carbons are both electrophile, those will react with the nucleophiles. So how can you tell whether a nucleophile will attack on the carbonyl carbon or do a conjugate additions? So it will attack with this carbonyl carbon or it attack with this carbonyl carbon. It depends on the nucleophile. If the nucleophile is hard nucleophile, that means Grignard reagents, organolithium reagents, if attack, they will attack in the carbonyl nucleophile, because this carbonyl nucleophile has higher charge density, electrostatic domination. So that's why Grignard reagents, organolithium reagents, those hard nucleophiles attacks in this carbon. But those who are the lower charge soft nucleophiles, that means organocreepers, Gilman reagents, will attack this carbon, because this carbon has lower charge density, orbital interaction dominated. So that's why the soft nucleophiles, organocreepers, thiols, and anolates attack with this conjugate carbon. So that's why this will form the conjugate addition. So here you see that the conjugate addition mechanism. In the first step, the nucleophile, which is pair of electrons in the copper CH3 bond. So here you see that the copper CH3 bond forms a bond with a beta position ketone. So this is our alpha position, this is our beta position. So we can actually go further, draw a resonance from where we can form AC carbon carbon bond place with the negative charge on the oxygen. So by this, the product will be the conjugate addition product. So our addition will be in this conjugate point CH3, that means meta positions. So this is the our reactions.